Thank you. Should I start over? For those of you watching in the recording, I have explained the sort of why cosmology is important, but if you don't believe me, that's okay. Anyway, this is a timeline that's showing you the beginning and then the end of the universe, where we are now, and kind of the spatial, what things might have looked like. And hydrogen shows up in all of these. At the very beginning, it's ionized. The Big Bang is kind of a hot quantum mess, but eventually it cools off, and you get that hydrogen and the helium. That's the green bit, and then it's just hydrogen for a while, and then well, nothing happens, and then stars, and then galaxies, and so on. At some point in there, most of the hydrogen gets ionized. I'll explain that more in a second. But the basic idea is if you can look at hydrogen, you can actually see it a lot. So how do you look at it? Hydrogen is a very simple atom. It is a proton and electron, and they are separated by about 10 to the minus 13 centimeters. They're very small. It's the smallest atom. Because of a slight quantum thing, like the splitting of the ground state of the atom because of the spin orbit momentum coupling of the electron, you get a little tiny separation in energy levels. Quantum mechanics says that if you have a separation in energy levels, you can emit or absorb a photon with an energy equal to the energy spacing between the levels. It so happens that there is a ground state energy splitting in the hydrogen atom, which has an energy difference corresponding to a photon of 21 centimeters in length. So usually, in physics 1 or whatever, you learn about maybe some of the transitions they give you, like Lyman alpha and stuff like that, like optical and infrared and UV photons. But this is a radio photon. This is huge. This is the smallest atom that you can make, and it's this foot-long photon comes wiggling out of it. It's the weirdest thing. That's messed up thing number 2 in this talk. It really bothers me that this happens. I mean, what does it look like? It's this big. Also, it turns out that the decay time constant of this state is inversely proportional to the frequency of the photon. So it takes forever for it to come out too. It really does come very slowly. It does not really, because that's not how quantum stuff works. But anyhow, it happens. And second thing about this is that it is a very precisely known photon wavelength. So if a hydrogen atom emits a photon and time goes by, the universe expands. This is a subtle hint here in this figure. You can see how this is kind of expanding like a cone. Well, that's the Hubble expansion. That's just the fact that literally the fabric of the universe is expanding because of that's just how it started off. And it does that. And when it does that, the photon itself stretches. So it travels to us through the universe as it travels. It gets stretched out. And if it's from far enough away, it could get stretched a lot. So you can actually map that redshift to how far away it was, and how far away it was also matches to a time. They're all basically the same thing. That's what we call redshift. So if it went from 21 centimeters to 2 meters, that's a redshift of 10, roughly. If an atom is a little bit further away, it travels a little bit further, gets a little bit redshifted more, and then travels on its way to us. So that means wavelength matches to distance. So now I can tune my dial. I know there's a 21 centimeter line that's been redshifted, and I can match that up to where it came from. And that's kind of like taking a core sample. By tuning my dial, I'm picking a time in the universe. Like that, just like drilling an ice core. And like drilling an ice core, I can do this a lot. I can get a spatial map of where did, I don't know, stuff fall from the volcano or something like that. Here's a simulation. Here's 3 simulations, actually. These are just, it's the how much hydrogen, how bright is it? That's the color. The x-axis is the same as the one I just showed you before, except it's probably reversed because time, cosmologists, people cannot agree which direction time runs. In this case, it runs from right to left. And then it's a slice, like a pie slice, like up through the universe, out to the back. It's a one-dimensional slice through the universe. And it's three different models, three different things that could have happened. And I'll talk about a little bit later what the kinds of things could change. But basically, it's, well, when exactly did stars form and stuff like that? But this is where your core sample is. So that means that here's a sort of wrap it all up summary. You have the early universe, stars turn on, eventually they are bright enough, and there's all those that they're at first they're so dim that their light is blocked by the hydrogen that is out there. But eventually they get brighter, and instead of blocking it, they burn it away. So they heat it up and they burn it away, and that's when these gaps start to form. And so at this point, Hubble can see them. But before that, they can't. And then as things keep going and reionization progresses, all the hydrogen between the galaxies is just burned away, and we get the universe that we have today, where we can actually see the galaxy next door, and it's not all foggy with hydrogen. But if I rewind it, I can give you some idea of what it might look like in hydrogen emission. Hydrogen is pink. You see that there's fluctuations because there's uneven matter distribution. So where there's more matter, there's more hydrogen. Also, there's temperature fluctuations. There's like the stars are heating things up and they're making the hydrogen a little hot, so it's a little brighter. And as that keeps going, eventually you start to see the ionization is happening. So there ain't no hydrogen where it's ionized; it's all gone. So you have places where you're now looking at gaps. So you get this really nice contrast where there's stuff between, like maybe far away from any stars, where there's just nothing there to ionize it, and you get these little islands, and then eventually even that's all gone. So that's kind of it in a nutshell. And the big picture, this is the big picture. So you have this sort of hydrogen where it's cool and not really, there's nothing happening, eventually some stars, and then eventually they're bright enough to observe with regular telescopes like JWST. But earlier times, you need something that can observe the 21 centimeter line to see anything. And some of the questions that you can answer are things like, how did the stars form? I'm just going to throw, I wanted to throw in a couple of questions that we're asking, and and you know what? There are a lot of these timelines out there, so I just threw a whole bunch of them on there because I think they're cool. So this is one of the central questions. How do you take a bunch of hydrogen and turn it into a star? Stars require carbon, nitrogen, and oxygen to burn. It's a fact. So if you just take a bunch of hydrogen and pile it up, you don't get a star, you get a black hole or a big explosion or something. And so really figuring out how we actually got a regular star like we had today is one of the open things. Another one is when? When did this happen? There's a lot of simulations that I've seen where people just throw out a redshift or a time or whatever you want to call it. Stars formed at, I don't know, 500 million years. And they just guess. Nobody knows. That's very frustrating. What were the first galaxies like? Were they nice places? Were they weird? No one knows. And this is one of the things that we're hoping James Webb will tell us, because we'll be able to get spectra from those galaxies that earlier, get these really the very first galaxies. But it's going to be tough. I mean, they draw that red arrow, that little white arrow, all the way out to redshift of 20. But boy, that's going to be tough. And then the last one this is the one that really bothers me and that keeps me going, is what is the universe made of? According to this chart over here, it's made mainly of pi, which I'm kind of secretly hoping is true, but it doesn't seem likely. One of the central discoveries of the last 20 years is that we don't know what most of the universe is by energy, dark matter, dark energy. What are these things? If you go back to really early times, that's kind of all there is dark matter and a little bit of hydrogen. It's all really close together too. So you might think that there might be some clue there about what's going on in a time and place that nobody has looked at yet. So that is potentially something that could turn out to be useful. And I'll touch on this a little bit more later. So onto HERA. HERA is a weird telescope. It is a bunch of dishes that are sitting on the ground, staring straight up. They have an antenna feed hanging over them. They're kind of like little mini Arecibos. The telephone poles are holding up the antennas, and the dishes are made of PVC pipe. It is low cost. It is a hardware store telescope. There are 350 of these dishes. That is a large number. It is one of the largest fully correlated radio telescopes in the world. It's a ton of collecting area and builds on a lot of the stuff that we've learned from first generation instruments, which I don't have time to tell you about today, but little experiments people have done all the way up to entire arrays that have been built. So this is the type of image that you might expect you could make given a perfect instrument. This is an image, this is another slice just on the sky now. It's, in this case, you've got, it's showing emission, but you could also look at it in absorption. Anyway, the trouble is it's really faint. Even with all that collecting area, even with 350 of those dishes, the collecting area is good enough to give us about 1.2 sigma on that predicted amplitude. It's not easy. But if we take a power spectrum, which is basically just a measure of how much RMS power, how much bumps are there on different size scales, we can do it. We estimate the sensitivity to be, if you throw in like a typical model, we get sensitivity estimates anywhere from 10 to 60 sigma, like huge, depending on the model. So this is on the left is an image. It's basically like the animation I just showed you, but now a real simulation. And it's showing you, this is actually the ionized regions. It's ionization fraction. On the right is a power spectrum. This is the estimation. This is basically, you can read it as the y-axis tells you how much power there is on different size scales, and the x-axis is size scale. So the very left part is 1 degree, big stuff, and on the sky, and on the right is about the resolution limit of the telescope, about 6 arc minutes. That roughly maps to on the left, distances between clusters, and on the right, between galaxies. So that's sort of just kind of give you a sense of where the size scales are. The other thing to note here is that as the process goes on, you can see the redshift up in the right-hand corner there of the image. You can see the shape changes. First, the largest scales drops. The whole thing kind of just drops straight down as you get less power on the left. But as the voids start to sort of combine and get bigger, you get big power on the largest scales, which makes sense. You have these big bubbles that are propagating outwards, and they're joining up, and they're turning into larger structures. And so you get a ton of power on large scales on the left-hand side, and then the whole thing drops away as hydrogen disappears. So you have you have both K modes, we'll call K modes. They're just basically size scales. And we also have redshifts. We have this sort of two-dimensional space that we can look at for the kinds of measurements that we might want to make. So I can, for example, pick a K mode on this plot and plot it versus redshift, just to see how different models might evolve as a function of redshift. Here's an example. So this is again, the same y-axis. It's the same measurement of power, but now I'm showing you versus redshift, and for a few different models. You can see there's huge differences. Depending on when you start galaxies forming, if they start them early, for example, you get a ton of power earlier. If you have some kind of weird cold dark matter annihilation or something weird like that, that could also inject a ton of power really early when the universe is small. So this tells you that if you can, and you can see the sensitivity curve there on that black steppy line there. So if something is bigger than that line, we'll see it, and if it's smaller, we won't. So if we don't see anything, we know it's more like maybe like the gold line and not like the red. That's kind of the game we're playing. So here are some actual data. Here's where we stand. These are going back to K now, so we're not looking versus redshift because we actually don't have very many redshifts yet. And these are all this is just one of those jumbled, everybody's throwing their data in and kind of showing you where things are. The gray, the sort of gray, dark gray, light gray thing at the top is indicating first and second generations, roughly categorizing of of telescopes and analysis methods. And that's just to show you that things are coming down. We're heading towards the blue, which are the simulations where we think things are. So this is a hard problem. You need a lot of sensitivity. You need a really precise array, and there's a lot of, as you can see from the blue, these are all different models. There's a huge variation in potential models for us to rule out. In fact, there are some that are even brighter that can get up towards 10 to the 4 in some cases, and so those are starting to put pressure on. So this is the sort of this is the point that we were at about a year ago. And now I'll wind back the clock a little bit and tell you just about HERA construction, which started in 2015, but then really got going a little bit in 2017. So HERA is in South Africa, just south of the Kalahari Desert, at the Square Kilometer Array site. This is one of the two major sites that are hosting the Square Kilometer Array, which is aiming to do this but better, basically. So we're formally a precursor to that. Another precursor is Meerkat, which is a more traditional VLA-like instrument that a lot of people are using to good effect. Right next door, that's our nearest neighbor. HERA is this circle down here. I'll zoom in on it. Is it going? Nope. It is going. So there's kind of the timeline. You're watching courtesy of Planet Labs. The array is you can kind of see it start to grow. Dishes are being added. You can see that gray blob on the left. That's where dishes are. We're about halfway done. In about 2018, we started testing really seriously. And in 2019, we had about 120 operational dishes. I'm going to tell you about data from 2017 when we had 60 dishes, but we've been keeping going. And just to give you a sense of where we are, in 2020, we completed the array dishes, but are still installing the electronics in some places. So we've been observing the entire time because it's more of an experiment than just a observatory, because there's a lot of open questions about how to build an array like this that we haven't answered yet. So this is a data set we took in 2017 with these dishes here. So this is a zoom in on the map showing you the dishes that are active. It's the bottom left corner of the array. On the right is an image that was made by a student, Tyler Cox, here at ASU. And it's showing you as sources, as HERA sits there staring at the sky, sources drift overhead. There are a bunch of stuff in the sky besides the cosmology. I won't talk about how we get rid of it, but basically it's pretty easy to filter out the foreground, relatively speaking, easy. Here is, I really want to give you a sense of how hard this is without actually telling you. So I'm going to show you. This is an example of our pipeline validation effort. So this is an effort that was led by Stephen Murray, postdoc in our group, who basically went around the entire collaboration, and every single one of these boxes was a step that somebody had built, and figured out how to connect them all together and run them in a way that we could test the inputs and outputs from every single one of them and make sure that there was no funny business. This is a huge effort to get together, and every single one of these is a squirrely cat that doesn't want to connect to any other boxes. So this is the kind of effort that it takes to make a precision cosmology project work. And the proof is in this thing here, which I'm not going to bother to explain in detail. This is a set of raw data on one of the columns is a set of raw data, and on the other column is a set of simulated data that came out of that pipeline. And I'm betting 99% of my audience can't tell the difference. I'm not going to ask you which one you think it is, because sometimes people get it right and prove me wrong about half the time. So the idea is you have a large, complicated instrument that you don't understand. You have lots of really smart people inventing all kinds of crazy algorithms to deal with it. And then you have to sort of have confidence in your result at the end of the day. We're generating something like 150 terabytes in this data set alone, and by the time we're done, it'll be about a petabyte per season. We can only do it once. We can only do our process thing once or twice. So you really got to be sure before you click the button. It's kind of like going to space. The other thing you have to do right is your data selection. You got to be really careful, because if you know what you want a lower power spectrum, you could pretty easily pick data that gives you that, no problem. So on the right, I'm showing you the sky in I don't know, like sort of flat world coordinates. The galaxy is the Milky Way galaxy there on the, it makes that sort of smiley face. And then HERA stares up at the minus 30 degrees latitude, right, ascension, or declination, sorry, and just watches the sky go by. We observe that white box, and then we had to decide, what do we want to pick to put into our measurements? And that's not an easy question, because you might say, well, we don't want to look at the galaxy, it's bright, and let's look at the quiet spots. And because the cosmology means that's the same no matter what direction you look. Remember that circle plot, the circle illustration I showed you? It's the same no matter where you look. But that's in the background. The foregrounds are, it's the galaxy and all kinds of other stuff. You also get to pick which frequencies you look at. So here I'm showing you the full band that we're observing. Now look, you look at the top, you can see the frequency that we're observing, and that's somewhere between 100 and 200 megahertz. But there's all kinds of stuff. So this blue curve is showing you where we had to flag because there was something. Flag just means say, don't use this data. There's all kinds of stuff up there. There's satellites, there's TV channels, there's FM radio, which is just off to the left there. It's all kind of, if you had something in there that happened to look like the EOR, epoch of randomization, 1 centimeter power spectrum, that happened to look like it, you wouldn't know the difference. So you might like to pick a region that is not corrupt. But how do you pick it without kind of lying to yourself? Well, you try to understand your data really well, and then you also have you have multiple people do it without talking to each other. Those are two very important things. So the first thing that we did was look at it really carefully, and we found something funny. So this is a power spectrum, but now in slightly different units, where instead of it doesn't matter what it is, the power spectrum. Think of it that way. There should be some EOR somewhere in there. On the left, so HERA and telescopes like it are polarized. They have dipoles, cross dipoles that observe one polarization, like an up-down polarization, and one like a left-right polarization. And you can talk about up-down and left-right, but you'll confuse people. But if you talk about Stokes parameters, everyone knows you're talking about polarization. The Stokes parameter is just a linear combination of different polarizations. So the I is the total power. It's like the average. Q is like, I don't know, sort of related to one of the polarizations. So we look at the power spectrum, we see, oh, it's nice and flat like noise. Noise is flat, that's good. We see a big old bump in the Q. It's polarized, it's a thing. And it's only there for certain sidereal times. Every night at the same sidereal time, there it is. It's highly polarized, and the bump moves with frequency. So these different curves are different frequencies, different bands, different chunks of the spectrum. It moves, it goes to, what can do that? And we scratched our heads longer than I care to admit, because it turns out it's a pulsar. Pulsars are highly polarized, and they have what's called rotation measure. Their polarized emission is coming to us through a magnetized plasma, which makes exactly that. I have to tell you, like, this might not seem exciting to you. Pulsars are everywhere. That we've known about them for a long time. One of the people that discovered them just died the other day, telling Jewish. That's how long we've known about them. Not that long. But we have yet to observe something, have yet to discover something with this instrument. This is the first thing we did not think to expect there, and there it was. So that was pretty exciting to actually see something. We don't see things a lot in our line of work. So, okay, so you go through carefully looking at your data, trying to understand it and make predictions based on evidence that have nothing to do with what you want to get. But you can also do a kind of a thing where you do a simulation. You take that big old yucky pipeline I showed you, and you just simulate the heck out of it. You run it, you make a thing that has a signal that you don't know what it is. You do a blind challenge test where you make a simulation that I don't know what it is, and you hand it to me, and I try to figure out what's in there. So another guy in our group, Matt Kolopanos, did this, and he's got a pipeline that is his own. He made it. It is not connected to anything inside the collaboration, and tried to figure out what it is. So this is the same units I just showed you. Turns out that the 21 centimeter signal shows up as a slight bump at low K beyond this big main thing here. It doesn't really matter what the details are. The point is, he didn't see it. It should have been in there, but we didn't know what the level was, and he couldn't see it. So then we went and had a little bit of a conversation, very carefully, sort of like a secret negotiation. People like negotiating, but they don't want to say what they want to pay for something, kind of like that. But we found out, we're throwing out these times in the simulation. That's it. And because we happen to know that the simulation was doing something stupid at that time. And sure enough, I'll go over there. Here, I'll use this. The black is one of the simulations, and the red is the other. You can see that they're different. One is significance, because you can tell because the error bars don't go through zero. This is a log scale, but see zero over here. So some things are consistent with zero down here, and this simulation is not, which means that we can tell the difference. We can tell in that really yucky simulation that makes data that looks just like the telescope whether there's something in there or not. This is about as technical as I'm going to get. Okay, this is the idea here is to really build the case that we can convincingly explain to ourselves that we're seeing something. So if I go back so now I can say, what did we see? Well, this is the answer. The HERA results from that first season are in big bold. So we can see that so redshift is in color. Redder is further away, and bluer is closer, roughly speaking. You see that the lower redshift at redshift 8 bin is pretty low, starting to get close to the models. The red one is less low. That's because at lower frequencies, the noise increases. I won't explain why, but it does. So one question you might ask, okay, so we're getting into the territory of, I don't know, factor of 5 or something within that dashed line model anyway. If the yellow was below that dashed line and it was still just a line, these are limits. These say there's nothing above this. If that yellow line went below that dashed line, it would mean that model is not true. It's not what the universe is doing. So it turns out there are a few models that actually do go above those yellow lines. Here they are. Here's what they kind of look like. Back to just looking at images again. One of them is if you have a situation where the universe is really cold, it'll be absorptive against the background CMB. And if it so happens that for some strange reason it gets really cold, big cold, but it doesn't have very big fluctuations. If for some reason it happened to ionize despite being cold, like you can imagine, it's hard to imagine, like some kind of a very fast ionization or something, I don't know. You get a big signal, and that is way above. You can see this bottom over on the right-hand side. I'm showing you the data. The black indicates the most, the weightiest point. It's heavy. And the blue and red are the power spectra of these models. You can see that they're above the data point. So since we don't have a data point with an error bar right around that model, it means it's not the one. So we rule that out. That's the kind of game you can play. You can sort of come up with toy models to try to figure out what's going on. You can also ask the question, what are the first galaxies like? When stars form, they tend to like in like a stars tend to form in clusters. A bunch of gas collapses into fragments and you get a bunch of stars. A lot of times they look like this. This is an X-ray binary. About half of stars form in binaries, I think, or something like that. And a lot of them, one of the stars is so big that it explodes and you get a black hole or you get a neutron star. And so the smaller star gets sucked in. And because of the way that the gas gets sucked in, it emits a lot of radiation, particularly X-rays. You get these X-ray binaries, and they're fairly uniformly spread out. They're kind of rare. They're out there. You could get, but in the early universe, if all the stars are forming all at once and they're mostly massive stars, you might expect a lot of them. Could you get a galaxy of these things? So to answer that question, you might build a model by taking a whole, like the typical, like one of these and making a galaxy of these. So on this plot over here, I'm showing you the luminosity of X-rays. So just how many X-rays are there per time a star forms. So if every star is an X-ray star, you would get a bigger number on the right. Our galaxy, or like the local universe, is the black line. And then if you were to make a whole galaxy of these based on what we think, and this is a simulation, a theory, it might be the dashed line. Our actual knowledge, we can sort of measure as a function of probability. Where do we think things are? We can think in a probabilistic way. And we might say something like this, where we don't really know. Our prior is basically flat. We don't know what this is going to be, because all we really know is that solid line. We might guess that it's a little bit to the right, somewhere around that dashed line. We can do a fit. Now that we have this HERA data, we can do a fit and put in a bunch of different galaxy models and work out which ones are most consistent, like a probability distribution function, basically. And it looks something like this. That means that it's a little bit to the right of that dashed line. So it kind of seems like that model is probably right. So that's what and there's other things too. You can go and find this paper down here. There's about 3 or 4 other really interesting things you can do. You can put constraints on some models of dark matter. Some of the crazier ones, ones that people really don't probably think are right, but new evidence is new evidence. And you can also put some kind of constraints on velocities. If things are moving around a lot, you get a much bigger power, and so you can put some limits on that. So like I said, this was data collected a few years ago while we were first just starting to build. Since then, a lot's happened besides the construction. The importance of X-rays, this sort of thing, has become increasingly more important. And in particular, it affects the very earlier times, like even earlier than we're observing now. So the very first stars form, and they have copious X-rays, and they heat up the universe. And so if that's happening, it could really change the timeline. So you can look at this. You can look at so this is yet another slice. Time is running from left to right. Blue is cold and red is hot. Blue being, I don't know, feels cold. The actual blue things are hot. So you can also take an average of the sky. You see how it's like generally blue and then generally red? Well, that maps, you can do this in an instrumental sense with a single antenna. And the interesting thing about the average is that it's limited. It can't get lower than about this red line, according to the standard cosmological model. So this is where the Edges Low project was observing. And a few years after we started construction, we had already started thinking about this time period, because if you look, this dip is really deep. It's really deep compared to later, like here. which is where the results I just showed you. Because it's so deep, it should be bigger. Bigger things are easier to rule out. Why don't we look there? That was a thought that was already rumbling around, and we'd already started planning to expand. So you can see this this band here that goes up to redshift 12. But then 2018, EDGES saw a dip in that rough area. There it is behind you, and there's some of the data. Look at the scale. The scale goes down to about minus 0.5. If you put that on this scale, it looks like this. It's deep. It's way deep. It's really deep. So deep that people started questioning cosmology and adding things, because it doesn't have to go below the red. You could also move this whole thing up by having some bright stuff behind it. There's a lot of ways to make it work. So not just because of this, but because it's going to be a deep thing no matter what, we ought to go look at it. We arranged to have an expansion. So we've expanded now our range of frequency coverage, which we do to get at some of these deeper models I showed you before, like way out here. So here's what the change looks like. On the left is the array using the feeds that we used to do the limits I just showed you. On the right are new feeds. These are broader bandwidth. It's really hard to make a broadband antenna, and so these are what you get if you try to do that. They're bigger. You can see that they're trying to go to longer wavelengths, and they have a lot of weird features. Like they have no back plane. They just don't see the sky above them for some reason. Here's how big they are. They're huge. They're hanging over the dish like this. And this is where we are right now. As of today, we have about 200 of these installed. We've, like everything, been slowed by COVID. And we continue to observe through construction. This is what the site looks like. You can see all of the construction stuff going on there. One thing I want to say, COVID's impacted all of us in different ways. It's been similarly bad in South Africa. They had their little bumps here, and generally haven't had it as bad as we have here, except maybe our last bump. This is case counts. Every time cases go above a certain level, we can't do things on site. It might seem like they're doing about what we're doing here, but if you look at the death rate, it's been quite, especially near the end here, it's been pretty hard on them. So the people on site have, through the entire pandemic, more or less, with some exceptions, been working and building and making it happen. You can see the enormity of the task they have here. They have to build all the dishes. They have to get all the antennas up. They have to plug them all in. They have to hook up the the insane network we've devised for them, and then basically be our remote hands, because we haven't been on site in over almost 2 years now. We've been building this telescope remotely. Normally, people they host us, grad students and postdocs and all of us that are helping around the world that are looking at the data. We go out and play with the telescopes. We actually tell what the heck is going on. We're looking at the data remotely. We haven't been there in a long time. So they've been really picking up a lot of slack, and I don't think can really get enough praise for the work they've done. So the data that I talked about today is available on our website. The power spectrum data is there. The papers, more importantly, the papers, if you want to read about the details, are also listed there. There's the main results paper, and there's also the main theory paper, which talked about all the stuff I just showed you. And then a bunch of stuff about systematics and things like that, and simulation and the validation and all that stuff is all there. They're all either in press, published, or under review. Here are some of the institutions that are involved and are funding. At ASU, the group is not small. Here are some of the people that have been doing a lot of the work. In particular, some of the people who I've highlighted here today. We've had summer students and and a lot of CC students, and a lot of, in fact, even some aerospace students and a few other people. I also want to throw out a thank you to Emory Riddle, who let us build a HERA dish on their campus, mostly so we could see how it went together, because again, it's far away and hard to understand, and we wanted our own. So they cleared a little spot in an arroyo, and the physics department lent us some students for the weekend, and we made it happen, and it was very, very useful. So I'll end there with a thank you to the department for asking me to speak, and to all of you for listening. We have a weekly coffee on Friday afternoons. If you're interested in stuff like this or anything else engineering or engineering science related, please come and join us there. You can, there's the list of past talks there on the website, and email me if you have any questions that I can't answer today.
Okay, we have time for questions. So let's start with folks in the audience first. Anyone? Don't be shy.
We have a microphone for her.
Yeah, wait for the microphone.
Okay.
Oh, there's one right here. So I was wondering, where is the funding for this project coming from?
It comes from the National Science Foundation, mainly, through their mid-scale program, and also from the Gordon Betty Moore Foundation, who have largely fronted for the low-frequency upgrade, the phase 2 upgrade. Also significant support from the South African Radio Astronomy Observatory, SARAO, which is sort of like the South African NRAO if you're a radio person in the US.
Okay. Who else? Do we have online questions? Okay.
First one is from Alyssa Walker. It says, could HERA theoretically pick up dark matter?
Yes. Yeah. Well, like I said, a lot of the interesting models that might explain a very deep absorption trough at higher redshift might have something to do with that. Also, it can show things like dark matter annihilation can have impacts all the way down through through the whole range of redshifts we might be looking at.
Okay. Let me ask a question. I get to, because I'm the
Yeah.
I want to know something more about the change in the shape of these antenna receivers that went from one to another and the second shape is just bizarre.
Yeah.
And there must be some reason for that.
Yeah.
Can you elaborate?
I can. So the change in so let me just pull up, where is that? Here, this thing.
Yeah.
So he's asking, why are these antennas so different? Like so the one on the left is actually kind of bizarre too. It looks a little bit more like, a thing you can understand because it's got arms, like an antenna, like a dipole antenna, right? But it's also got those big discs. It looks kind of like a UFO or something, right? It's a big thing too. It's about this big. This disc itself is about this big, and the antennas kind of go out to here. And then it's got that tuna can behind it, which kind of makes sense because you don't want it to catch the radio somehow, right? So that's a sleeved dipole in 2D. The disc broadens the resonance. So if you just have a dipole antenna, you get one frequency. It resonates. And anywhere outside of that frequency, it don't resonate. You add stuff around it, it broadens that resonance. So you get this broadband frequency response. And if you go up to here, say, you want, look down here at the bottom. We want to be able to observe from 60 to 200 megahertz. That's a huge fractional bandwidth, really wide. So in order to make that work, you have to do weird stuff like put those disks. The other thing is called, so that gives you for like 100 to 200 megahertz. That fractional bandwidth, let's call it 1. Going to the other, this other antenna, we wanted to get to 2 fractional bandwidth. This is called a Vivaldi antenna. It's basically like an inside-out quadridge feed horn, if you know what that is, but you probably don't. But it's like a horn. The active element is kind of like this swoopy part in the middle. Yeah. And you can imagine, you can think of it as like you think of it like a little antenna at every one of those distances. So you get all of the distances. Okay. So you get all of the frequencies. Okay. Is kind of a way of thinking about it. You could also make it with a horn, like a literal horn, with no loss. It would basically be the same thing. It's just lighter, but we can drill speed holes in it.
Got it. Okay, anyone else here?
Roger Windhorse has a question. He's going to ask it on Zoom. Go ahead, Roger.
Thank you, Danny. Great talk. So can the power spectra from HERA give us a clue where the potential overdensities are at redshifts bigger than 10 so we can prepare to point at those regions with JWST?
The power spectrum, no, but with a higher order spectrum, yes. And so a lot of people have been working on this problem. There's a nice paper from one of our former postdocs, Adam Beardsley, who looked into this specifically and found that if you can make, and so I said that you can't image, but you can image. And if you can filter foregrounds, pretty good. So you don't get a great image because it's been really badly filtered, but it's got a really weird PSF basically. You can still get a really good probability map, especially if you have a detection in the power spectrum. So you can actually sort of say what the model is underlying. If you have a detection and you kind of know what's going on, and you can kind of image, then you can make a probability map saying, go look here. You should expect to see a void, because that's what you probably want, is a void, right?
Right. Yeah, that'd be great. Thank you.
That's the dream, man.
All right, let's take one more question here, and I think we'll hang on.
I can repeat the question. I think you asked, when do I project the next data? Yeah. So we're in the process of when we did this upgrade, when we added these funky antennas, that's the only visible part. But actually, the hard part was we also upgraded the digital systems and the analog system, everything. We switched out everything, and we're in the process of doing the last commissioning on that now. In the best possible scenario, we will observe this season. The season is when the sky is cold at night. And that could lead to a data set. And we have the machinery of our pipeline there. So we won't have to spend 3 years or whatever it was, 4 years getting it together. So maybe 2 years after that. I'm hopeful. It's a small team, big data.
Okay, so let's thank our speaker again, and thanks for your questions.